What if the problem isn't how big 3i Atlas is, but why it refuses to stay the same size, the same object? Two sets of data, two different realities. In December, scientists released a new calculation of 3i Atlas based on non-gravitational acceleration. Instead of estimating size from brightness or shape, they measured the subtle forward push created when gas escapes from the object's surface. That single calculation suggested a body roughly 1 kilometer wide. But this result immediately conflicted with months of earlier observations. From May through September, the object's orbit was tracked with extreme precision. And during that entire period, no measurable non-gravitational acceleration was detected. Given how sensitive those measurements were, the object should have been at least 5 kilometers wide to remain that stable. This was not a minor disagreement that could be explained away. One set of data described a compact object weighing only a few 100 billion kilograms. The other required a body 5 times larger and more than 100 times more massive to behave the way it did. What makes this contradiction unsettling is that both conclusions come from real observatories using established methods. There is no obvious instrument failure, no single dataset that can be casually dismissed. This is not random noise in the data. It is a structured contradiction, where science follows its own rules correctly and still arrives at two answers that cannot both be true. If the data is right, then what exactly is wrong? Scientists did not calculate the size of 3i Atlas by seeing it directly. They inferred it from something far less intuitive, an invisible push acting on the object as it traveled through space. This push is known as non-gravitational acceleration. And it appears when gas escapes from the surface and creates a subtle rocket-like effect. The strength of that acceleration depends on two physical factors. The first is how much gas is being released every second. The second is how fast that gas is leaving the surface. Together, these two values determine how strongly the object should be nudged forward along its path. In the case of 3i Atlas, those gas properties were not guessed. They were measured directly by the James Webb Space Telescope, which detected both the speed of the escaping material and the total mass being lost over time. With those numbers in hand, scientists could calculate how much force was being applied to the object. Once the force is known, physics works in reverse. If you know how hard something is being pushed and how much it accelerates, you can determine how massive it must be. From that mass, assuming reasonable density values, the diameter naturally follows. This chain of reasoning is grounded in basic momentum conservation, not speculation. This approach is not experimental or exotic. It has been used for decades to estimate the size and mass of comets that are too distant or too small to resolve clearly. In other words, the method itself is considered reliable. If this technique has worked so well before, why does it now disagree so sharply with earlier measurements? From May through September, 3i Atlas was monitored continuously by more than 200 observatories around the world. This was not a casual watch. It was one of the most precise orbital tracking campaigns ever applied to an interstellar object. The measurements were sensitive enough to detect incredibly small changes in motion. The positional accuracy reached levels where even tiny deviations caused by weak forces should have stood out clearly against the background of normal orbital behavior. Yet, throughout that entire 5-month window, scientists detected no sign of non-gravitational acceleration at all. The object followed a clean gravitational path, as if nothing were pushing on it from within. What makes this absence so striking is the sensitivity of the detection limits at the time. Those earlier observations were more than 300 times more sensitive than the acceleration measured later in December. If even a fraction of that force had been present earlier, it should have been unmistakable. The only way to reconcile such silence with the physics of outgassing is mass. A much heavier object would experience far less acceleration from the same amount of escaping gas. In other words, the lack of detectable acceleration strongly implies that 3I Atlas had to be far more massive during that period. Why would a force that becomes measurable later be completely absent when our instruments were most capable of seeing it? As 3I Atlas moved closer to the Sun, one explanation began to look tempting. Comets are known to lose mass rapidly when solar heating intensifies. Ice turns directly into gas. Dust is lifted off the surface, and material streams into space without ever becoming liquid. This process can dramatically change an object over a short time, near perihelion. Mass loss is not gradual. It can accelerate quickly, stripping away surface layers and exposing new regions that were previously sealed beneath ice and dust. Under this scenario, it is possible that 3I Atlas was significantly heavier during the earlier months of observation. A larger mass would naturally suppress any measurable acceleration, keeping the object's motion stable from May through September. But the numbers create a serious problem. To bridge the gap between the early silence and the later acceleration, the object would need to lose tens of trillions of kilograms in a relatively short period. That is not a small erosion. It is a transformation on a scale rarely seen. Even among highly active comets, such extreme mass loss pushes far beyond what most standard comet models comfortably allow. It would require either an unusually fragile structure or a composition that responds to solar heating in ways we do not yet fully understand. If 3I Atlas truly shed that much mass so quickly, then what kind of object was it before the Sun ever touched it? Acceleration is only measurable when it changes the motion we are watching. In orbital tracking, that means the force must push the object along a direction that alters its predicted path. If the push points elsewhere, it can exist without ever revealing itself in the data. Gas escaping from a comet does not always act in a neat, symmetric way. If most of the material vents sideways, perpendicular to the direction of travel, the resulting acceleration barely affects the orbital position we measure. The force is real, but its signature becomes almost invisible. Comets are especially prone to this behavior because their activity is rarely uniform. Jets often erupt from localized regions rather than the entire surface. Some areas remain dormant while others vent aggressively, creating an uneven distribution of thrust. Rotation complicates this further. As the object spins, the orientation of active regions changes. A jet that once pushed harmlessly sideways can later rotate into a direction that produces a measurable effect along the orbit, even if the total amount of gas remains the same. This means a small change in orientation can completely transform what we observe. The force does not need to grow stronger. It only needs to point in a different direction to suddenly appear or disappear from our measurements. If a real force can hide in plain sight simply by pointing the wrong way, what does that say about how much we truly trust what we see? Once all conventional explanations are laid out, a different kind of question begins to surface. If this behavior is not the result of error, noise, or poor modeling, then what category does it belong to? An interstellar object is not required to behave like the comets we know, because it did not form under the same conditions or evolve within the same system. The acceleration associated with 3I Atlas appears late, fluctuates in strength, and depends strongly on direction. It is not steady, not symmetric, and not consistently detectable. From a data perspective, it behaves less like a simple physical response and more like a signal that resists stable characterization. The inferred mass does not remain fixed either. At different stages of observation, the object seems to demand different values to explain the same underlying physics. Early on, it must be massive to remain dynamically quiet. Later, it must be far lighter to respond so visibly to outgassing forces. What makes this pattern unsettling is how neatly it avoids resolution. Each time the data begins to point toward a clear conclusion, another parameter shifts. The object never violates physics outright, but it also never allows a single interpretation to settle. The result is a dataset that feels strangely optimized to remain inconclusive. This does not imply technology, intent, or design in any literal sense. It points instead to behavior that avoids predictability. A system that passes through, interacts just enough to be noticed, and leaves behind questions rather than answers. If an object were to pass through our solar system without leaving a clear physical signature, would we even recognize that anything unusual had happened? This story does not end with a revelation. It ends with a confrontation. Science did not fail when it encountered 3I Atlas. It was tested. And what was tested was not a single theory, but the assumptions that quietly sit beneath everything we measure. 3I Atlas forces us to look at the foundations of how we interpret data. Density, symmetry, stability, predictability. We assume these ideas apply universally, because they usually do. But this object reminded us that nature is not obligated to behave according to our expectations, especially when it comes from beyond our own stellar neighborhood. What makes this encounter uncomfortable is not the lack of answers, but the realization that a real physical object can exist outside our measurement comfort zone. It can pass through our solar system, interact just enough to be noticed, and still resist being pinned down to a single explanation. The silence in the data is not empty. It is dense. It is information that does not resolve easily. Information that demands patience rather than conclusions. In that silence, science learns where its edges truly are. And that may be the most valuable legacy 3I Atlas leaves behind. Not a discovery we can label, but a boundary we can now see more clearly. If an object can cross our solar system without agreeing to be understood, are we ready for the next one? If you value stories that explore the edge of science rather than rush to easy answers, consider subscribing to the channel. We do not chase conclusions here. We listen to the data, even when it stays quiet.